The hodopelagic zone is the deepest ocean region. It's found from a depth of about 6,000 to 11,000 meters and exists in long, narrow topographic V-shaped trenches. The deepest of these ever discovered is the Mariana Trench. And despite all logic, life survives in these darkest depths. And the creatures here have evolved to be exceedingly freaky. From the ghostly to the terrifying to the absolutely gigantic. The giant squid. The giant Japanese spider crab. The big red jellyfish. The king of herrings or fish. The Greenland shark. And the giant isopods. These animals are all examples of deep-sea gigantism, the tendency that deep-sea animals have to be substantially larger than their shallow water counterparts in waters intensely cold and dark. Why do these leviathans emerge? Is it an eerie coincidence of the deep dark sea, or a feature of life in this inhospitable landscape? Below 400 meters. Food becomes quite scarce in the ocean. As sunlight tapers off, photosynthetic algae and plankton disappear too. And without this crucial part of the food chain, life gets markedly harder for deep-sea animals. Instead, most of them have to rely on detritus that rains down from shallower waters, a phenomenon called marine snow. Marine snow is mainly composed of dead plankton, fecal pellets, and bits of rotting corpses that fall to the seafloor as fine particles. Some animals rely directly and completely on marine snow. The vampire squid, for example, has special adaptations to help them better catch and eat the falling particles. Two long filaments extend from their bodies to capture any that drifts past them. In their habitat, 900 meters deep, marine snow is the backbone for all life in the deep, but it can't support a great deal of biomass. The number of creatures in the deep is sparse, and the food web is strained. Many animals don't eat marine snow directly, but rely on eating those that do, and thus the pressure of predation is extremely high. Any small fish, crustacean, or cephalopod has a big target on its back from any larger predator, and for this reason, it became evolutionarily advantageous for animals to get rid of this target on their back to transition from being a prey animal into a top predator. Enter the giant squid, both an icon and an enigma of the deep. By the turn of the 21st century, the giant squid remained one of the few extant megafauna to have never been photographed alive. What we know about the giant squid largely comes from specimens that have washed ashore. It wasn't until 2004 that the first photographs of a live giant squid in its natural habitat were taken in the twilight zone, at a depth of about 1,000 meters. And while we may not know much about these mysterious creatures, we do know that they are huge. The largest individual ever found was 13 meters long as a school bus, and weighing 175 kilograms, compared to the majority of squid, which are no more than 60 centimeters long. These giants are truly exceptional. Scientists believe that, by having such a tremendous size, they're left with few predators, and allows them to comfortably prey on deep-sea fish and other squid species, which they grab with their two extremely long tentacles. But as impressive as the giant squid is, it is not the largest of the deep-sea squids. The colossal squid, sometimes called the Antarctic squid, is the largest invertebrate in the world. They're shorter in length than the giant squid, at only 10 meters, but can weigh between 500 and 700 kilograms. Lurking in depths over 2,000 meters, it's easy to imagine such a massive creature as an aggressive top predator, darting through the water, snatching prey, and dominating its adversaries, ripping sailboats apart, etc. But this squid teaches us something else about deep-sea giants. They aren't necessarily the dominating, predatory force we imagine, because with their large size comes something else, and extremely slow metabolism. The colossal squid takes something called Cleaver's law to the next level. Cleaver's law states that metabolism doesn't scale linearly with body size, as you might predict. A horse that weighs 1,000 times more than a mouse doesn't require 1,000 times more energy. Instead of metabolism scaling linearly with body size, it scales with an animal's mass to the 3/4 power.